Welcome again.
Today we consider the following applications: calculation of cell potential using standard electrode potentials, prediction of whether a reaction is spontaneous or not using electrode potential values, and finally the determination of standard free energy, the Gibbs free energy changes, using standard electrode potentials. Let us begin by considering this reaction. Here we can see that tin 2 ions lose electrons, and in so doing they are oxidized from tin 2 to tin 4, and iron 3 gains electrons, and in so doing is reduced from iron 3 to iron 2. To identify the half equations occurring at the cathode and the anode electrodes, you should use the data booklet provided in the examination. And here you can see that tin gains 2 electrons as it moves from tin 4 to tin 2. If you are required to show a movement from tin 2 with the loss of 2 electrons to become tin 4, then this equation simply needs to be reversed. Similarly for iron 3, as it gains an electron and is reduced to iron 2, you have this equation, and if you need to show the reverse, where iron 2 loses an electron and becomes iron 3 and is oxidized, then you simply reverse this equation. The standard electrode potential associated with each of these reactions is provided in the data booklet. Is oxidized from tin 2 by the loss of 2 electrons to tin 4. Oxidation is loss. And iron 3, by gaining an electron, becomes iron 2, and in so doing is reduced. With this information, we can now calculate the standard potential in volts for this cell. Using the equation, the electrode potential equals the cathode, or the right-hand electrode, minus the anode, or the left-hand electrode. In this case, iron is the cathode, and tin the anode. Iron is the more positive of the two values. Plus 0.77 minus positive 0.15 gives a cell potential value of 0.62 volts. Again, it is important to note that cell potential is an intensive value, and it is not affected by quantity. So the fact that 2 electrons were accepted by 2 moles of iron 3 to give 2 moles of iron 2 does not change the calculations as given in the data booklet, and the standard electrode potential for iron 3 as it becomes iron 2 would remain as 0.77 volts regardless of the number of moles of iron that is converted. But as we move to work with the Gibbs free energy, it is important to note that the Gibbs free energy delta G is an extensive property. This means that calculations will be affected by the number of moles. So now we're ready to determine delta G, the standard change in Gibbs free energy at 298 Kelvin in kilojoules for this electrochemical reaction. And then, based on this answer, we can comment on the spontaneity of the reaction, or its tendency to occur without the input of energy. Spontaneous reactions tend to occur without the input of energy from the outside, as opposed to non-spontaneous reactions which require the input of energy. A spontaneous reaction typically loses free energy from the system and is characterized by a negative value for the Gibbs free energy. If this calculation produces a negative value for delta G, then it shows that the reaction is spontaneous. And to determine delta G, we must use this equation. Delta G equals negative N times F times the cell potential, where negative N is the amount in moles of electrons transferred in the balanced equation, and F is the Faraday's constant, which equals 96,500 coulombs per mole, and E is the standard cell potential, which was calculated earlier using the values provided from the data booklet. Noting that delta G is an extensive property, and the 2 moles of iron that have been used in this equation need to be considered, as 2 moles of electrons are required to reduce iron 3 to iron 2. 96,500 is the Faraday's constant, and 0.62 volts is the cell potential. This produces an answer of negative 119,660 volts coulomb. And the unusual unit volt coulomb is produced because we multiply potential by charge to determine energy. But the SI unit of energy is the joule, which is equivalent to volts coulomb, with 1 joule being equal to 1 volt coulomb. So rounding up the answer to 2 significant figures and putting it in scientific notation gives an answer of negative 1.2 times 10 to the power of 5 joules. And here it's important to note the negative value for delta G, which symbolizes spontaneous reaction.